Hello students, I am Mr. Adinath D. Badar, Assistant Professor, Department of Chemistry, late Pushpadevi Patil, Arts and Science College, Risod, Dist, Washim. Today I am going to discuss topic for B.Sc 3rd, semester 5th, unit 1st, that is coordination compound, lecture number 2. In the previous lecture, we discuss the basic of coordination compound and terms involved in coordination compound. In this lecture, we are going to discuss Werner's theory of coordination and Sidgwick's electronic concept for complexes, that is effective atomic number. So firstly, we see what is the Werner's theory of coordination. So to explain the structure of coordination compound, important attempts were made by number of scientists like Berzelius, Graham, Claus, Bulstan and Jorgensen, but none of them could explain the satisfactory structure and properties of this compound. Later on, in 1893, Alfred Werner, professor of chemistry at the University of Zurich, put forward his well-known theory for the coordination to explain the formation of compound and its structure of complex. His work in this field, he was awarded the Nobel Prize and now rightly called the father of modern coordination chemistry. So firstly, we see the assumptions of Werner's theory or postulates of Werner's theory. So first assumption is the central metal or the metal atom in coordination compounds always show two types of valency. These are primary and secondary valency. The primary valency related to the oxidation state and the secondary valency is related to the coordination number. The primary valency always related to the oxidation state of that CMI or central metal ion, and the secondary valency is related or correspond to the coordination number of that central metal ion. The number of secondary valency is fixed for every metal atom. It means that coordination number is fixed. The metal atoms works toward satisfying both its primary and secondary valency. A negative ion, always negative ion, satisfy the primary valency. On the other hand, negative ion or positive or neutral molecule satisfy secondary valency. Now the next assumption is the secondary valency points towards a fixed position in a space. This is reason behind the definite geometry of the coordinate compound, means secondary valency always corresponding to the geometry of complex. For example, here let us consider in the case of metal ion having 6 secondary valency, these arrange octahedral around the central metal ion, means the geometry of this complex is octahedral. If the metal ion has 4 secondary valency, these arrange in either tetrahedral geometry or square planar geometry around the central metal ion. Therefore, we see that the secondary valency determines the stereochemistry of the complex ion. On the other hand, the primary valency is non-directional and just corresponding to the oxidation state of that central metal ion. Now, for the verification of his theory assumption, he was performed the experiment on the basis of conductance and number of mole of AgCl precipitate by using cobalt with series of amine having the composition like COCl3 6NH3 COCl3 5NH3 4NH3 and 3NH3 and determine the number of mole of precipitate and conductance, and this is a structure and the color of complex. For example, here COCl3 6NH3, here the number of mole of AgCl precipitate is 3, number of ions per molecule is 4, and the conductance is high. These are the structure CONH3 by 6Cl3. These all 6 amine satisfy secondary valency and corresponding to the geometry, that is octahedral, and all these chlorine satisfied primary valency and corresponding to the oxidation state, that is +3 oxidation state, and the color of this complex is yellow. Now in the second composition, here COCl3 5NH3, in this compound 6 mole of ammonia are used. In this composition only 5 mole of ammonia are used. Hence mole of silver chloride precipitate is equal to 2, number of ions per molecule, that is 3, and the conductance is medium. Structure of complex compound is CONH3 by 5 Cl, and these are Cl2. This ammonia satisfied secondary valency. This chlorine satisfied secondary as well as primary valency, and this chlorine satisfied primary valency, and the color of compound is purple. Now the fourth composition is COCl3 4 mole of ammonia. Here mole of AgCl precipitate is 1, number of ions per molecule is 2, and the conductance of composition is low. Structure of complex compound, that is CONH3 by 4 Cl2 Cl minus or Cl. Here the color of compound is green, and the last complex or last composition COCl3 3NH3, that is 0. The mole of AgCl precipitate is 0, number of ion per molecule or conductance is 0, and structure of complex CONH3 by 3 Cl, and the color is violet. This is a neutral complex. These are the neutral complex. Here these 3 chlorine are corresponding to primary valency. Here these 2 chlorine are corresponding to primary valency, means ionizable. Here 3 chlorine are ionized to give 3 mole of AgCl and 4 mole of ions. Here only 2 chlorines are ionized to give 2 mole of AgCl and 3 number of ions. Here only 1 chlorine are ionized and gives 1 mole of AgCl. Here all 3 chlorines satisfied secondary as well as primary valency, means here no chlorine molecule are ionized. Then the number of mole of AgCl is 0, number of ion per molecule, that is conductance, is also 0, and these are the neutral complex. These are the neutral complex. Now here the diagram clearly shows here structure of first composition, that is COCl3 6NH3. In this compound the coordination number of cobalt is 6, that is secondary valency 1, 2, 3, 4, 5, 6. Coordination number is 6. Secondary valency are occupied by ammonia molecule. The chlorine ions are bonded to the cobalt by 3 primary valency. These are 1, 2, 3 denoted by dotted line. These 3 chlorine satisfied primary valency and these 6 amine satisfied secondary valencies. All these chloride ion are precipitate on the addition of silver nitrate. The total number of ion in this case is 4, 3 chloride, 1, 2, 3 and 1 complex ion. Thus the complex may be formulated as like here CONH3 by 6 Cl3 minus. Now the next composition is COCl3 5NH3. In this compound the coordination of cobalt remain 6. 5 positions occupied by amine 1, 2, 3, 4, 5. 5 amine satisfied secondary valency and the sixth position occupied by this chloride ion. This chloride ion exhibits a dual nature as it held by secondary as well as primary valency. The total number of ions in this case is 3, that is first chlorine, second chlorine and complex. The total number of ion is 3, 2 chloride ion and 1 complex ion. This complex may be formulated as like here CONH3 by 5, 1 chlorine are enter inside the square bracket and remaining 2 chlorine retain at position or ionize. Now the next composition is COCl3 4NH3. COCl3 4NH3. In this compound the chloride ion, 2 chloride ion exhibit dual character or satisfy both primary and secondary valency. It will gives precipitate with silver nitrate corresponding to only one chloride. This chloride only precipitate with silver nitrate to give 1 mole of silver or AgCl. The total number of ion in this case is only 2. For example, this one chlorine and one complex, one chloride ion and one complex ion. It may therefore be formulated as here CONH3 by 4, 2 chlorines are enter inside the square bracket and remaining 1 chlorine, these are ionized to give 2 ions and 1 mole of AgCl. Now the last example or last composition COCl3 3NH3. In this compound all 3 chloride ions satisfy primary as well as secondary valency. Here there is no precipitation of silver chloride for due to no ionizable chloride here. All 3 chlorine satisfied primary as well as secondary valency and these amine satisfied secondary valency. So therefore the complex behave as neutral or non-conducting molecule. It may be formulated as here CONH3, all 3 chloride are enters in square bracket. Here the variation of color with the changing composition. Here first composition shows yellow, here second composition shows purple color, here third green and fourth that is violet. In addition to the complex of cobalt, Werner prepared large number of complexes with other metal ion. He also explained the formation and behavior of all other metal complexes. Now the next theory, Sidgwick's electronic theory, interpretation of coordination compound. Due to the advancement of electronic theory of valency, various scientists have tried to give a sound base to the Werner's theory of coordination in light to electronic theory of valency. The main aim of this theory is that every atom tries to acquire electronic configuration of the nearest gas, and while doing so it may form complexes like octet rule. Sidgwick in 1927 extended the Levy's concept of two electron covalent bond, that is coordination bond, for the explanation of complexes or complex compound. The assumptions are summarized here. So first assumptions of Sidgwick's electronic theory is the ligand has at least one such atom which carries lone pair of electron to donate the central metal ion to form complex. The second assumption is a ligand donates the lone pair of electron to the metal called as acceptor and ligand called as donor. As ligand donate the lone pair of electron, it is called as donor, means Levy's base, and metal ion accept lone pair of electron, so it is called acceptor or Levy's acid. Hence the secondary valency of metal ion is satisfied by ligand. The third assumption is the bond between donor ligand and acceptor metal is very strong, and it is called coordinate bond. This is much the same as covalent bond, however it is represented by an arrow directed from ligand to the metal ion like this. This bond is called as coordinate bond, that is directed from ligand to the metal ion. Now the fourth assumption is primary valency is a electrovalency, that is equal to the number of electrons lost by central metal atom. If an atom has N as a primary valency, it will lose N number of electron and form a positive ion of charge, that is N plus. These primary valencies are satisfied by negative ion. On the basis of the assumptions above, the structure of complex CONH3 by 6 Cl3, these are the structure. These are the central metal atom, also called as acceptor and also called as Levy's acid, and these are 6-amine ligand, also called as donor and Levy's base. Now we see the Sidgwick's concept of effective atomic number, also called as EAN rule, effective atomic number rule. Through the application of electronic concept of formation of coordinate bond, Sidgwick give a effective atomic number concept. According to him, effective atomic number is the number of electron associated to the central metal ion in a coordination compound. Many cases, effective atomic number is equal to the atomic number of next coming inert gas elements. In some cases, EAN, that is effective atomic number, is not equal to the atomic number of coming next inert gas elements or nearby them. These are the exception for effective atomic number rule. EAN can be calculated by using a simple following formula. Here, effective atomic number EAN is equal to Z minus N plus 2 into Cn, that is Z is the atomic number of central metal ion. Here N is the oxidation state of central metal ion. 2 and Cn, that is the coordination number of central metal ion, number of ligand attached to the central metal ion. Thus EAN of the complex CONH3 by 6 plus 3 can be calculated as here atomic number of cobalt is 27, oxidation state, that is small n of cobalt, here plus 3, this plus 3, coordination number of cobalt ion, that is Cn is equal to 6, these 6 amine are directly attached to the cobalt, then the coordination number is equal to 6. Putting this value in the above equation, we get here effective atomic number is equal to Z, that is atomic number, minus oxidation state, that is N, plus 2 into number of ligand is 6, that is coordination number is 6. So 27 minus 3, 24 plus 6 into 2 is equal to 12. 24 plus 12 is equal to 36. This 36 atomic number of krypton, that is the inert gas or noble gas. Now some other examples here, effective atomic number of some metal complexes. Consider the atom Fe atomic number 26. These are the complex ion FeCN6 minus 4. Here oxidation state is plus 2. Here coordination number is 6. Here oxidation state, how to calculate oxidation state? Minus 6 is equal to minus 4, minus 6 is equal to minus 4 means plus 2. This 6 minus 6 is equal to minus 4 means plus 2. Here coordination number is 6. So EAN is equal to 26 minus 2 plus 2 into 6, that is 12, that is 36, that is the atomic number of krypton. Now the second example is cobalt. Here atomic number is 27. These are the complex ion CONO2 by 6 3 minus. Here the oxidation state of cobalt is plus 3. Then the coordination number is 6. So 27 minus oxidation state, that is 3, plus 6 into 2. Here number of ligand is 6 into 2, that is 12. So 36, that is the atomic number of krypton. Now the another example, atom is copper, atomic number is 29. These are the complex CuH2O by 4 plus. Here the oxidation state of copper is plus 1, coordination number of copper is 4. So 29 minus 1 plus 8, 4 into 2. Here ligand are 4. So coordination number 4 into 2, that is 8. So the total is 36, that is the atomic number of inert gas krypton. Now the another example, PdCl6 minus 2, that is oxidation state is plus 4. Here coordination number is 6. So atomic number 46 minus oxidation state 4 plus 6 into 2, that is 12. So these are 54. These are the atomic number of inert gas xenon. Next inert gas xenon. Now the another example is here Fe26, FeCN6 minus 3. Here oxidation state is 3 and coordination number is 6. So 26 minus 3 plus 12, that is 6 into 2, 12. This is 35 and This example does not obey the effective atomic number rule. This example does not obey the effective atomic number rule, and these are the exceptional cases. Now here another example is like same. Here 28 atom is nickel, atomic number is 28. These are the complex hexaamine nickel second. Oxidation state is +2. Here the coordination number is 6. So 28 minus 2 plus 6 into 2, 12, that is 38. These are also high value and does not gives a next inert gas value. So this nickel hexaamine nickel second does not obey the effective atomic number rule. Now the next is drawbacks of Sidgwick's theory. Sidgwick's theory cannot explain the following points. There will be improbable accumulation of negative charge on a central metal ion which accept the lone pair of electron from ligand. This seems unluckily. It does not explain the stability of complex in which inert gas configuration is not achieved. It does not explain the directional nature of coordinate bond. The electron donated by neutral molecule like water, ammonia to the central metal ion belongs to the 2s2 pair which have no bonding characteristic, and to excite them to higher level would acquire more energy than is usual available in bond formation process.